Okay, this is the last video of chapter 4, and so far we learned how to calculate the range, the interquartile range, and the variance and the standard deviation, right? So in this video, in the last video, I will be more qualitative. I'm not going to use much algebra, but instead I'd like to explain what they mean, what they are, why we need them. So standard deviation is so important. So let's think about what it means. First, the larger the standard deviation is, the more variable the data are. So measure variability, right? So like for example, but the problem is when you have a standard deviation of 10, so you calculated the standard deviation and it was 10. What does it mean, right? So that is kind of tricky because when I say the expected value is $10, for example, then you understand what it means, right? Expected amount, return is $10. That is more intuitively understood. But the standard deviation of $10 is not easy to understand. But actually, it does mean anything. I would say standard deviation is a unit, not something like meaningful. Like for example, when I say like my height is 57 inches, then what does that mean? Well, that just means 57, right? 1 inch does not have much meaning. So then, what is the definition of $1? Dollar does not have definition. It is just a unit, right? So 1 degree in temperature, what does it mean? I don't know what it means, but we don't know, right? So we use those units, but we do not know what they mean. Similar, standard deviation is a unit of the distance from the center. So it's like inches, right? So the distance is like miles, inches. Oh, it is kind of relative unit. So for example, this standard deviation can be used as a unit when data are in different units, right? So we are comparing two like students, for example, and we would like to compare them who is better. For example, the first student has a GPA of 3.4 and another student has GMAT score of 600. Like say you are screening applicants for a graduate school. And then the problem is the scales are so different, right? In this case, 600 is greater than 3.4, but that doesn't mean anything. Just it's like 20 times greater, like 200 times greater, doesn't mean anything, just different scales. So then what we are going to do here is we are going to compare them first with the respective mean. The mean average GPA is 3.15. Average GMAT is, for example, 560. For example, this is just a numerical example. And then compared to their respective mean, the first student is above average, and the second student is also above average, right? Then what we get, these numbers are the distance, the deviation, right? This is distance. But again, the scales are different. It is 0.25 in GPA, but it is plus 40. It's like more than 10 times, like not more than like 40 times greater, nearly. So it doesn't mean anything, right? The units are different. Here comes the standard deviation. I'm going to include the standard deviation information here. Of course, they're fake numbers. So then, this is the distance. Numerator is distance of that student from the mean, and divide that by standard deviation. That gives you another distance, 1.25. This is a distance in the unit of standard deviation. Similarly, the second student's score is 600, which is plus 40 from the mean. That is the deviation for the second student, but that is divided by its standard deviation, right? then you get 1.33. That is a measure, like a distance from the mean in terms of standard deviation. So now these units are comparable, right? Because they have the same scale of standard deviation. So this is the standardized test score called z-score, right? So I believe you must be familiar with this kind of standardization somewhere, like, and this is how we can understand the standard deviation. And it does not have any meaning, right? But when it has meaning only when you think it relative to something. It's a unit, okay? So this is commonly used standardization later, like we'll use this later. So you have original variable x, and we are going to transform into z by subtracting the mean and then divide the difference by the standard deviation. That captures how many standard deviations each observation deviates from the mean, right? So it's measured in standard deviations. That's the unit, right? Of course, it can be negative if it is below average, and it's positive if it is above average. And it is a measure of relative standing. So instead of the test score itself, this standardized test score might be more informative to understand your ranking, your relative performance. Okay. All right. So let me add one more thing. So one hidden keyword that I am kind of emphasizing again and again is transformation of random variables. Random variable. Okay, so we learned x, and I change xi into xi minus exi, and when you calculate the variance, we took its square, or from here we can calculate standardized score, right? So these guys are missing information from the mean, right? Because we are subtracting the mean, so we have additional information that is not contained in the average, right? And then mathematically, it would be interesting to think about extensions of them, right? So extend the square to cube. What happens if you take exponent of 3? Or what happens if you take exponent of 4? That is possible. You can keep going, but usually up to here is taught in the textbook. Okay, they are here. So the variance is coming from the transformation of square of the deviations, and then skewness is cubed deviations, right? Just natural extension of the same transformation. And what it is, the difference here is, the variance is always positive, but skewness can be negative or positive. It may be negative or positive. So skewness captures literally which side the distribution is skewed, right? So if skewness is 0, the distribution is about like symmetric around the mean, about the mean. And if the skewness is positive, that means it is skewed to the right, skewed to the greater side. So there are outliers on the right side tail, greater side. If the skewness is negative, that is the other way, outliers on the left side, so smaller side. So of course, the greater the skewness is, there are more extreme outliers on the right hand side. Okay, histogram wise, this is, so center is here and here, and we call outliers that are far away from the mean, and outliers are on the left hand side that we call left skewed or negatively skewed. In this case, skewness measure will be negative. And also, remember, these extremely small outliers will drag down the mean more than the median. So mean will be smaller than the median. And left tail is long. So they are the same. So to describe the shape of this kind of shape of distribution, so distribution skewed to the left, so we are going to calculate skewness or mean and median. Just symmetric right side outliers will cause right skewed, positively skewed, right long tail, and then mean is greater than the median. Okay. As the outside outliers exist, then we use skewness. And the mode is usually in the textbooks, mode is introduced as a measure of center. So the measure of central location includes mean, median, and mode, introduced as a set, triplet. But I don't agree because I've never seen mode used as a center that often, right? So this definition is not wrong. Definition is most frequently occurring value. When you make a histogram like this, so usually the peak is mode, right? This has the highest probability at the peak, right? So in this example, as you can see, it is not center. Center should be somewhere in the middle, but it's just the highest peaking point may not be at the center. But the mode is more often used to describe the shape of the distribution. I think this is how I would suggest you to understand the mode. For example, these are unimodal distributions. That means there is only one peak. It's naturally decreasing away from the mode. So either direction from the mode, it's decreasing, right? So that is unimodal. And most of the distributions in practice are unimodal, right? But in some strange cases, there might be bimodal distribution. There are two modes, peak is here and here. Of course, the center should be here. So mode is definitely not the center here. But clearly, peaks are here and there, left and right. So this means this is bipolarized case, very weird case. So it's of its interest, right? And then we call bimodal distributions. And extending this idea, we may think of multimodal distributions when the histogram looks like this: peak, 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 peak. We just call multimodal. Something weird is going behind this data. Okay. So this is mode, and this is another extreme. There is no peak. It's just flat, completely flat, and then we call this uniform, right? So distribution has no specific mode, so we call that uniform distribution. Okay, this is all we do in chapter 4, and so as a separate online lecture, you are going to learn Excel how to use Excel to calculate the summary statistics. So summary statistics on Excel will calculate those measures by simple function, simple table. So please watch that too and do the quiz. Thanks for watching. See you next week.